We're in our solutions notes. This is for those of you with myself and Mrs. Mitiga. We're on page number 44. You're going to need your set of reference tables. Please open your reference tables to table G, please. All right, let's get started. All right, so table G is a solubility curve. And again, this is page number 44 in your notes. And we're going to need our New York State reference tables, reference table G. All right, so solubility curve is a graphical representation to determine the amount of solute. So remember from our notes, solute is what we're trying to dissolve, usually the smaller amount, at 100 grams of water. So this is basically, we're going to compare everything against this kind of standard amount of water that can dissolve at various temperatures. So we know from our factors that influence how fast something dissolves or how much something dissolves is going to be largely based on temperature. So the higher the temperature, the more we can dissolve, typically. All right, so to show how different substances can dissolve amounts of solutes at different temperatures. So whether temperature is going up or going down, we're going to be able to look at the relationship between temperature and solubility, which is the amount of solute that can be dissolved in that 100 grams of water. All right, so this is what table G looks like in your reference table. So I'd like to so as you are now should be looking at your reference tables in table G, a couple things I want to point out on table G, right? So solubility, right? So that's going to be how soluble something is. And we have here the solubility is in 100 grams of water, right? So that's our standard amount of water. And now here is our temperature. And you're going to get probably like a plus or minus 2. This graph looks really busy, but we're only ever looking at one line at a time. You're looking at a point in relation to a line, or how much more you could add to get up to a line. So basically, if I give you this point, let's making up a number here because I just like that number, 130 grams of a substance at 20 degrees Celsius, right? So 20 degrees, read it up to 130. So that's a point. And now I might ask you about potassium iodide up here. Or I might ask, how does this point relate to that line? Or I might ask about sodium nitrate over here. How does this point that I did over here, right? How does that point relate to this line? Right, so that's what we're going to be using on table G. So now on table G, and then I know my little menu bar here is in the way. So let me hide that. Okay. All right, so I'm hiding my little meeting controls over there and move myself up there. All right, so what is a saturated solution? So when you think of the word saturated, something should come to mind, because I'm sure you've probably heard this term before in some area. So saturated means the maximum amount of solute that can be dissolved in a solvent at a specific temperature. So basically, the maximum amount is going to make this solution full. I like to think of the word saturated meaning full. No more will dissolve other than that amount at that specific temperature. This again is how has relation to reference table G, right? So you should be looking at that reference table as we're talking. So each curve on table G, right? So all of those lines that we saw on that graph represent a saturated solution at a certain temperature. So each curve basically also means each point on the curve represents a saturated solution. Basically, that means the solution is full. That means it is the maximum amount of solute that's going to dissolve at that temperature. So now we have unsaturated solutions in relation to table G. So now unsaturated basically negates the saturated solution. So if the saturated solution is full, no more will dissolve. Anything else you add in there? So let me just put that up in here. So if you add more solute to a saturated solution, it's just going to sink to the bottom. or basically not dissolve. Most solids would sink to the bottom, but basically not dissolve. So now an unsaturated solution contains less than the maximum amount. That means more can be dissolved. So this is referencing any point below the line on table G. So on table G, any point below a line that we're talking about of a specific substance is going to be an unsaturated solution. And what happens if we add more solute to an unsaturated solution? So if I add more solute, let me go back. If I add more solute, right, at a certain temperature, right, just keeping the temperature the same. If I add more solute, it will dissolve up to a point and then up to the saturated point. And then at which point it reached saturation, no more will dissolve, and you try to add more and it's just going to sink to the bottom or not dissolve. So now we have saturated, so saturated is full, unsaturated is not full. And now we have super saturated, right? Our prefix super means above, right? Superman is like above men, right? Superfluous, right? Anything you see with the prefix super kind of like literally defines as something that is like above or better. I'm not going to call a super saturated solution better, but it's above saturated. So that basically means more than the maximum amount of solute is dissolved. And a solution, to get a super saturated solution, we have to heat it extremely high, and then the solute is basically forced into solution. And so this would be referencing any point above any of the curves on table G. Right, and so a super saturated solution is a solution that tends to be unstable. So I'm just going to write this here, unstable. If you try to add more solute here, the solute will what we call crystallize. Right, so that means that it's going to come out of solution. And so all of a sudden, if you have a supersaturated solution, you add a crystal or a little bit of more solute, and then all of that extra that made it supersaturated is going to come out of solution as crystals. And then you're going to end up with a saturated solution with stuff floating around or sunk at the bottom. Okay, so let's take a look here at how are we going to use this whole reference table G business. Let me just move over there. Okay, so if a question has 200 grams of water, so remember I said 100 grams of water is our standard amount of water. So that's basically comparing all of these substances in the same volume of water, right? We do need to have a control. But if I have double the amount of water, I can double the amount of solute, right? So then whatever I get on table G, whatever number, I would then multiply by 2. And now if I have 50 grams of water, which is half of my standard value, that means I'm going to have to take whatever value of solute, right, the grams of solute that I can find, and I'm going to divide that by 2, right? If I had 300 grams of water, what do? Multiply by 3. If I have 25 grams of water, I would end up dividing by 4. So this is why you really need to read your chemistry questions really carefully, because if the question says something other than 100 grams of water, you need to know whether or not you need to divide or multiply by whatever factor based on 100. And I've never seen them ask anything other than maybe like 200 grams of water or 50 grams of water, you know, maybe once or twice the 25 grams, but you're not going to be asked something ridiculous like, 34.8 grams, like, no, nothing like that. It would be one of the factors of 100 that you should be able to do pretty easily. All right, let's take a look at some solubility problems. Okay, so how much potassium chloride? So let's just circle this potassium chloride. All right, because now when I go back to my reference tables, I am looking at potassium chloride, and that's the only one I'm looking at. So how are you supposed to know which one potassium chloride is? Well, this is why we've already done this unit where we did our, formulas and naming. So first of all, I need to look for something with a potassium in it. And if I don't know the symbol for potassium, I have reference table S to help me with that. So where do I have 2, 3 things with potassium on there. So, but I want potassium chloride. So that would be this one. Where are you, potassium chloride? There we go. See, it's got this little arrow is pointing to it. And so I'm going to just kind of make my line purple, right? So that maybe we can focus a little bit more on this line. Oops, as you can see, I'm not really good at drawing. So now you should also have your notebook out. So I'm not going to go back and forth to that question because I have the question in my notebook open. You should have your question in your notebook open. The question says, how much potassium chloride is needed to make a saturated solution at 50 degrees? Okay, so at 50 degrees, I'm going to find 50 degrees. And so now, according to our notes, every point on this line for potassium chloride is a saturated solution depending on the temperature. So at 50 degrees, I read this and I read it up and I find the point. And then again, that's my dumb pointer thing. And then I read across, right? So I find my point and I'm going to read, oops, sorry, hold on everyone. No, there we go. So I read, I'm just gonna draw the line. I'm gonna read, oh, Mrs. Davis, my goodness. All right, so apparently I have messed up the pen. All right, so reading up to potassium chloride, and then now reading across and over. So it's right about there. So now this goes from 40 to 50. About halfway through the box would be 45. So it's a little bit less than 45. You probably would be given a plus or minus 2. So let's go with, I don't know, maybe 43 or 44. How's that sound? All right, I like that idea. Let's go with that. All right, let's go to that problem. All right, so at 50 degrees, right, I located 50 degrees on the x-axis. I located the potassium chloride curve. I followed up and I read the y-axis. Okay, so 42. All right, so, I was a little bit off. Too, right? But I said you get like a plus or minus 2 on this graph, right? You would read it a lot easier on your reference tables, with a regular pencil. Remember, my tablet looks like this. So when I'm drawing, I'm looking at the screen and not looking down here. So it makes it a little bit trickier with the pen. A lot of hand-eye coordination here. Okay, so let's look at 95. All right, so going back to your reference, going back to that question. All right, so now we want to go to 95 degrees. So 95 degrees. And see, I told you I can't even draw a straight line. Right, so 95 degrees is this point right there. And now when I read across, right, so then I want to say that's probably like around, and again, this is why my pointer is a little bit tricky, right? So it's going to be somewhere between 50 and 60. And then of course, if this is a multiple choice, it's going to be pretty obvious. I'm not going to give you like, 52 and 53. You would only have one value that's really close. All right, so let's go ahead and let's go back to where we were. All right, right, we said that was about 55, right? This little symbol here means about, approximately, right? Plus or minus. Remember, we have those uncertainty significant figures. It's just based on what we're drawing. All right, let's go on to another problem. So we have a solution at 60 degrees contains 70 grams of potassium nitrate. Identify 2 ways it can be made a saturated solution. All right, so I'm going to go to my graph, right? So let me just go back to my graph. And I'm going to just get my little eraser button here so that I can just erase. And we'll just take a peek over here. Okay, so we have 2 ways we can make a saturated solution. And we have 60 degrees and 70 grams of potassium nitrate. So I have 60 degrees. So let me take my pen. And let's choose green. So I have 60 degrees. And I have potassium nitrate, which is wherever it's up here, right? This is our potassium nitrate. So at 60 degrees, potassium nitrate can dissolve this amount of substance, right? That's at about 105. Wow, now that's kind of interesting, right? So if a solution's at 60 degrees, contains 70 grams of potassium nitrate, identify 2 ways it can be made a saturated solution. I think it's already a saturated solution, but let's just see. Wait, 60 degrees has a potassium nitrate. I gotta go back here. 60 degrees and 70 grams of potassium nitrate. Oh, Mrs. Davis. This is what happens when you do this at like 5 o'clock on a Friday. Okay, sorry guys. Okay, so I have 60 degrees and I have 70 grams. I was pointing out that 105 is where it is saturated. I didn't read the question very carefully. See, teachers make mistakes. 70 grams of potassium nitrate. All right, so 70 grams is here, right? 60 grams is here. So I'm going to find that point, and that point is right here, right? X marks that spot. So this is not saturated. How do I know it's not saturated? Because it is below this line, right? If I have any point below this potassium nitrate line, and this point right that I hear is below that line, this is unsaturated. So in order to be saturated, I need to add this much, right? So from 70 up to about 105. So then I would do 105 minus 70. That's going to give us our saturated solution. So we have definitely more practice problems in this unit. You're going to have to use this table a lot, and we're going to do more practice. I want to point out a couple of other things on reference table G that I'd like you to draw on your reference table G. And let's go with our pen. Okay, so on reference table G, the couple of other question types that you might be asked is identify which of the following are gases. So I'm going to tell you which ones are gases, and you see if you can kind of figure out why it's a gas. NH3 is a gas, right? So NH3 is a gas. SO2 is a gas. And HCl right here is also a gas. So let's look at the relationship between most of these lines. Most of these lines are curving upwards, right? As temperature increases, solubility increases for most of these lines. There are 3 lines where it goes the opposite, right? We're sloping downwards, which means we're showing an inverse relationship, which means as temperature increases, solubility, with the amount of that can dissolve, decreases. Like, let's look at how steep this NH3, this ammonia line is. I can dissolve 90 grams in 100 grams of water of ammonia at 0 degrees Celsius. But then now as I get up towards the warm water stage at 90 degrees Celsius, I can only dissolve 10 grams, right? So that's a very big difference. Remember, so gases have an inverse relationship. As temperature increases, the solubility of a gas decreases. So our 3 gases are very important. On this table, like we did before with our point, any point below a line is considered unsaturated. So since I like to draw up here at the top of the screen, let's look at this potassium iodide. So if I put a point right there, and I say at 10 degrees, because that's 10 degrees, and 100 grams of potassium iodide, is this solution saturated or unsaturated? So at 10 degrees and 100 grams, this point is below this potassium iodide. That's an unsaturated solution. If I said sodium nitrate, let's take a look at sodium nitrate up here. So that means that I'm looking at this line that slopes downwards. So at the same point, at 10 degrees Celsius and 100 grams of sodium nitrate and 100 grams of water, this point is above this sodium nitrate line. So then that point is supersaturated for sodium nitrate. And now when you have a point on a line, now that means that we have a saturated solution. So if I said, I don't know, let's find like a nice easy, nice easy point here. Let's look at salt water. All right, salt is actually, sodium chloride is really not that soluble. So now at 90 degrees, so let's look down here, 90 degrees, how much sodium chloride do I need to add to make a saturated solution? So saturated means this point right on this line right there. So then at 90 degrees, I can add up to 40 grams of sodium chloride, and that would make a saturated solution. Any point below that, so if I did a point here, that would be unsaturated to sodium chloride. Right, so that really just sums up reference table G. In our next set of notes, we're going to start looking at some concentration, and we're going to do a little bit of math. Right, thank you for joining me today, and I look forward to doing our next video together.